All right, so we'll go ahead and get started today. So thanks everybody for coming out amid the sort of remnants of the blizzard from yesterday. It's good to see you. So in today's lecture, we're going to be talking about convolutional neural networks, which really are one of the core layers for all of the image processing networks that we use within robot perception, at least the deep learning-based variants of robot perception. But before we get into that content, I just want to do one quick reminder that Project One is due tonight, so at midnight. So I thought there were a few questions on EdSem about like collab limits coming up. I would say one big important reason why you should always make sure to start the projects early is because you don't want collab usage limits to come at the very end. What you can do in the meantime to develop, if you run into a collab issue, is if you move the data to the CPU, you can then, all of your collab then will run on the CPU and not the GPU. But come up, if you're having issues with usage limits for today's deadline, come see me after lecture and we can try and help resolve some of them. But with that, let's kind of get into convolutional neural networks. So in last lecture from Tuesday of this week, we started talking about backpropagation. And so we saw how for the actual application of gradient descent when it comes to training our classifiers and our neural networks, backpropagation is an algorithm that will let us efficiently compute the kind of required components, those gradients, for our weight updates. And so we saw that the two kind of pieces of backpropagation was first setting up some complex algebraic expression, which is our neural network, as a computational graph. And then the second component of backpropagation was the actual algorithmic steps that would take in that computational graph and then compute the downstream gradients, which is what we'll ultimately be using for our parameter updates, by the matrix vector product of our upstream gradients and our local gradients. And so the issue, though, which we didn't kind of have time to talk about, was that the classifiers that we've been looking at up to this point, so the linear classifiers and then also the fully connected neural networks, they've been treating our input images as just a column vector of numbers, right? And so then the parameters that would be operating on that input images are correspondingly like a column vector of numbers. And so in some sense, our classifiers up to this point are ignoring some of the spatial structure that exists inherently within image input. And potentially we could have better solutions, either that are more efficient computationally, or maybe that could even represent better classification models by creating a new operation, a new neural network operation that will try to respect some of the spatial structure within images. And so that ultimately is what the convolution layer is going to allow us to do, and it's going to be the focus of our lecture today. So as a brief recap about the kind of core components within fully connected networks, we saw that there were fully connected layers, which we were treating as this 2D matrix of weight parameters. So in this figure, it's the W1 weight matrix and this W2 weight matrix. And so we saw how if you stack those layers together, you can increasingly get deeper and deeper networks, which hopefully can achieve higher and higher level accuracy. But the second core component that we needed in order to ensure that our networks were modeling nonlinear classification problems, we had to insert these nonlinear activation functions after each one of our fully connected layers in order to ensure that we get that nonlinear decision behavior. And so similarly, for convolutional neural networks, we're still going to be using those two core components, but then we're also going to be introducing in today's lecture 3 other layers that are used for building up really kind of the core of our perception models from the standpoint of image processing. So we're going to talk about first convolutional layers, and then we're going to look at pooling layers as a way to downsample our images. And then finally, we'll spend a little bit of time, but probably more time in next lecture, talking about batch normalization and how that layer can improve the training performance for our deep networks. So to start out today's discussion, let's first go back and look once again at fully connected layers, and then introduce this idea of a convolution operation in relation to the fully connected layers. So you'll recall that for our image classifiers that we've been working on in the projects, we were treating this, what is naturally a 3-dimensional volume of data in the form of an image. So let's say that we're working on color images, And in our props data set, for example, those color images are each 32 pixels by 32 pixels in the height and the width. So our classifiers up to this point have been taking in that volume of data, which represents an image, and we first flatten it into a feature vector, right, of just pixels. Our classifier then would take this weight matrix, so this 10 by 3072 matrix of parameters that are going to be learned using gradient descent. We would do the matrix vector product between our weights and the input image, and then we'll get out some set of scores, right, one score for each of the 10 possible classes that would represent our classifier's decision. And so if we were to sort of introspect what actually each of those components of the output represents, right, so at each one of those 10 numbers, each one of those numbers represents the dot product between one of the rows of our parameter matrix and the entire image vector. Right, so it's that dot product is in some sense measuring, then we remembered kind of like the similarity between what we might imagine is like a template for each of the 10 possible classes, where that template is stored as a row of our weight matrix. And so the one important thing to point out then is that that template, or like the individual rows within that weight matrix, for them to make their classification decisions, they're going to be comparing the template with the full image. So they're never going to consider like only maybe sub-portions of the image and then ignore other parts. They're always being given that full image as input. And so this is in stark contrast to a convolution layer, which is inherently not going to be considering the full image to generate its output. So if we consider a single convolution layer, let's say that we're working with the same image data. So it's still going to be like an RGB color image. So we have 3 channels of depth, and it's still the same spatial size. So let's say 32 pixels in height and 32 pixels by width. But what we want our layer to do, instead of just producing just a single output classification vector, is instead we're going to try and have it kind of like search for where within the image most well aligns with a given filter. So let's say that in this case, we're using a filter that has 3 dimensions in the channel size so that it will fit over the three channels of our color image. And then it's going to be sized in the spatial dimensions of 5 pixels by 5 pixels. So maybe this is a relatively small feature. Maybe it's like an edge. And we want to search for where within the image does this edge kind of most appear. And so what the convolution operation is going to do is it's going to treat this filter as sort of a sliding window. And it's going to slide this filter across every possible spatial position of our input image, and then take a dot product for every one of those spatial positions where it would overlap with the image. And that's going to then represent our desired kind of feature map. So a couple of important things to first point out is that when we're talking about convolutional filters, the dimension of the filters in the depth, so in this case the 3 channels for color, always has to match between the filter's shape and the input tensor's shape. So in this case, both of our filter and our input image have dimension 3 in that channel dimension. So the actual underlying operation then of this kind of sliding window, this convolution, is let's say that we're operating within like a specific portion of our image, and we're wanting to measure, okay, for this portion of the image which is highlighted in the figure, how well is this feature being detected there? Like how well is maybe this edge being detected at this specific position? So what we do is we take our filter, we align it with that sub-portion of the overall image, and then we take the inner product between all of those overlapping elements. So the elements between the portion of the image at this spatial position, and also the elements within our filter, so within that 3 by 5 by 5 filter. And so we can think about then the resulting single number that we'll get by performing just this kind of operation within the overall convolution as being the dot product between 2 75-dimensional vectors. So it's this one number output that we're going to get for this inner product is going to be the result of an inner product between the filter treated as like a column vector and the sub portion of the image at this spatial location treated as a column vector. So in that sense, this one activation number that we're getting is similar to what a fully connected layer was giving us in the past, right? It's just a single dot product. But if you imagine that we were to perform this dot product operation by sliding the filter across all the spatial dimensions in the height and the width, what we would get is an activation map of size 28 by 28 by 1, corresponding to all the possible spatial locations in the image where this filter would be overlapped with during the convolution. And so what this activation map in some sense is going to be representing then is for a given filter, how similar is that sub-window in the original image aligning with the filter for a given spatial location, right? So the first spatial location within our activation map will correspondingly be sort of looking at a specific receptive field in the image, which is at the upper left, let's say, of the original image. And then you can sort of reason that as you move down one dimension of the spatial activation map, you're then asking how well does our filter match with these other spatial locations in the image. But we wouldn't be just limited to one filter, right? We could instead imagine performing this same convolution operation, so the same sort of sliding window inner product operation, using a second filter. And maybe the second filter is trying to detect an edge oriented in a different direction. And so then you can imagine now we would have two 28 by 28 activation maps as output. But of course, we wouldn't just be limited to two filters. You could keep adding filters for this single convolution layer, which might be trying to match these sort of different patterns that you might expect to see in an image that might hopefully be useful for our classification task. So let's say instead that maybe our first layer of this convolutional network is going to use 6 filters, where each of those filters is going to be a 3 by 5 by 5 window. And correspondingly, what we would expect to get as output from our convolution is going to be this stack of feature maps, where each feature map is 28 by 28. But in total, we have 6 that are going to be sort of looking for unique features in this original input image. So in addition to that, one thing that's useful is just as we saw for fully connected layers, we'll usually add a bias to our convolution layers to try and give them additional free parameters that they can learn during training to hopefully improve their ultimate classification performance or their feature extraction performance. And so what that looks like is we'll have a single element within our bias vector for each of the filters within our filter bank. So in this case, what happens is so within a convolution, you'll first perform that sliding window inner product operation. And then for each of the activation maps that we get as output, before returning them as final output, you'll add a bias vector with the same dimension as the number of filters you have in order to produce then the final output. So this is how bias gets incorporated into the convolutional networks. And so one interpretation, like I was kind of describing them in the past, was you can imagine that at every single one of the spatial positions within our activation maps, it's trying to represent how well does a specific filter kind of align with the image at this corresponding spatial location. But another way we could interpret the output that we're getting from a convolutional network is we're going to say at every single spatial position within the image, I'm now going to sort of summarize that original pixel or even the region around that original pixel with a vector of learned features, right? So in other words, like you could take one position within our activation maps and you'll get a 6-dimensional vector in this case. And that 6-dimensional vector would hopefully be summarizing in terms of these features. So in some sense, in terms of like a transformed basis, what is being represented in that original image at this corresponding spatial location. So that's another interpretation that you can use for trying to understand what these convolutional layers are learning and representing. So given that this is how a convolution is defined for one image, right, we looked at stochastic gradient descent as being defined as a training algorithm over a batch of images, or like a random sample of images from our overall training set. And so this idea of a convolutional layer will extend to batches of images. So if we have 2 images as input, instead what we'll have is we'll treat that as a volume of data that's 2 images, so that's the batch dimension first, then by 3 channels for the RGB, and then still the 32 by 32 spatial dimensions. And so correspondingly, if we wanted to run our convolutional layer on this batch of images, you can imagine first applying the convolutional layer to the first image that you have as input and producing your first activation map as output, and then applying that convolutional layer to the second image as input and arriving at a separate activation map, a second activation map as output. And so importantly, one property of convolutional layers in the batch sense is that the activation maps that you're getting for the different images are independent of the 2 images that were passed as input. So what that means is that these algorithms, these layers can be implemented in parallel, and you can have a really substantial speed up for applying the convolutional layers on different images in parallel. And so for the purposes of our training, that's going to make a big difference once we start to actually implement these algorithms. Okay, so generalizing this a little bit further, we could maybe consider cases where we don't just have RGB input always coming as input to our layers. Yeah, question? So the question was, if we're adding a bias, shouldn't the output dimensions increase by 1? And so the answer is not quite. So what happens is this: when you add the bias term to our sort of intermediate activation maps, which are internal here, what's happening is you could think about the bias vector as sort of being broadcast to all of the spatial locations for each of the activation maps. So in other words, we have one bias term for our blue activation map, another bias term for our green activation map. And so what happens internally within this layer is first we do the sliding window for each of our 6 filters. So we'll get 6 by 28 by 20, like a 6 by 28 by 28 activation map. But then when it comes to adding the bias, we only add like this single element, like this single scalar bias term for this blue element to the entire first activation map at every spatial position. So and then you would do the same thing for the other 5 dimensions in your bias vector. So we'll still have a 6-channel spatial map as output. So given this, though, it's not going to always be the case that we're operating with, let's say, RGB, like 3-channel images coming as input, right? So maybe you have an RGBD camera on your robot, so you have 4 channels. Or maybe you're trying to apply these layers to not even necessarily to images, but to some volume of data that's even beyond 4 dimensions, right? So it turns out that this discussion of convolutional layers can actually extend to an arbitrarily shaped input in terms of the channel depth, which could, as we'll see on the next slide, can be used for stacking these one on top of another. So to generalize what a convolutional layer does, let's say that we have some data that's coming as input which has the following dimensions. So it still has some batch size first, so let's say n examples. But then the channel dimension is abstracted away as just this number of channels coming as input, and then some height and some width of the input data. The filters then are going to be defined in terms of how many channels was coming as input. So we're going to require that our filters kind of fit over kind of overlap with all of the input channels. And then we can control how many output channels we want. So that's sort of a tunable hyperparameter of these layers. In addition, and that's going to control how many of these sort of individual features that we have access to. So in the last slide, the channels out was 6, but you could increase that or you could decrease that depending on the problem that you're trying to apply the layers to. And then correspondingly, what we will expect to see as output in terms of the size is the same number of images, let's say in our batch, or the same number of examples in our batch, so n. But now we're going to have potentially a transformed number of channels based on the number of filters that we have in our filter bank, so C out. And then we're going to have some height and width, but this could potentially be changed. So depending on the size of the filter, the constraint that your filter sort of overlaps with a portion of the image will mean that you're potentially losing spatial dimensions as you apply these filters. So in the last case, for example, the original input was 32 by 32, but because our filter size is 5 by 5 in its spatial dimension, we're going to correspondingly lose essentially 4 pixels in the height and the width in the output just based on how we're defining the sliding window. And so we get a smaller output than what our input was in the spatial dimensions. And we'll talk more about the math of how to calculate those kind of coming up, those changed spatial dimensions. But OK, so having now generalized this definition of what a convolution operation can do, one important realization is we could start to treat convolutional layers the same way we were treating fully connected layers in our discussion of linear classifiers using fully connected layers. So what we can imagine doing is taking, let's say, our original input, which has like 3 by 32 by 32 image. We could first pass it through our first set of our first convolutional layer, which had 6 filters. And now we'll have this transformed intermediate sort of hidden feature representation, which is going to be 6 by 28 by 28. And then we can imagine passing that through a second sort of separately learned convolution layer to produce some additional intermediate features. And you could keep kind of chaining these together, right? So you could keep appending additional convolutional layers, let's say further, like as not shown on this slide, to transform your data even further. And so the reason why you might want to do this is kind of similar to what we saw in the case of linear classifiers, where by having these additional feature transformations, hopefully we'll be able to model more complex data more accurately. And so I think so one interesting question is, as in the way that we've described the convolution up to this point, can anyone think of a reason why potentially stacking the convolutions in this way, exactly as we've shown on this slide, might have sort of a downside? One thing that you might recall that might sort of get some ideas going is that in the case of linear classifiers, we saw how without any activation function in between the layers, we were left, by composing linear transformations, your result is still a linear transformation. And so it turns out that actually in the case of the convolution operation, it's also a linear operator. And so as a result of that, if you just chain together linear operators, the result is still going to be a linear operator. So if you work out the math, it actually turns out that without any intermediate activation functions or other nonlinear functions in between these convolutions, just chaining together convolutions by themselves results still in a convolution because you're composing those linear transformations. So instead, what we'll normally do is we'll insert some nonlinear function, the same way we did for a fully connected layer, in between the individual convolution layers, so that we can model those nonlinear relationships in the data that we're interested in. And so typically ReLU is also one of the standard activation functions in the case of convolutional layers, just as it was for fully connected layers. So most of the time you'll see, when you look at network architectures that are published, you'll see ReLU as a common choice for activation functions following a convolution. Okay. Let me pause and just see, before we look at kind of ask this question about what convolution layers are learning, let me pause and see if there's a sort of any potential issues notation-wise or unclarity about how the sliding window is being applied. Oh, yes, there's a typo on this slide. This should be 26 by 26. Yes, thanks for pointing that out. I'll fix that. Right, it's 6 channels, so it would be like a 6 by 1 vector. Okay, so let's ask this question of what do these convolutional filters learn? What are they actually trying to model? Similar to how we were asking the same question in the cases of our linear classifier and our multi-layer perceptron, we can try and understand this. So you'll recall that in the case of the linear classifier, we were treating every row of that weight matrix that was being learned as sort of a template, like a kind of a template for a pattern that the model was trying to classify. So for our props data set, when we actually looked at what those learned templates looked like, we would see a figure that would look something like this. So for each of the 10 classes, the model is picking up at a global, like using a kind of global view of the input image, some sort of representative seeming example or template of what that class actually looks like visually. And in the case of the multi-layer perceptron, what we saw when we inspected the learned weights was kind of a similar concept, but now instead of just one template per class, there were these multiple templates that were maybe distributed across classes, right? There wasn't like one template was exactly one class. But based on the activations of some given input image and this bank of templates, the final classification score was ultimately being decided. But importantly, like just as in the linear classifier case, all of these templates, because of how we define the multi-layer perceptron, were still global with respect to the input image, right? So they're still like a 32 by 32 by 3 vector of numbers that are learned. In contrast, though, our convolutional filters, as we're seeing, are not defined over the full input image, right? So in this case, for example, like our convolution filters just had a 5 by 5 spatial dimension. So they can't possibly be representing those same templates. So it turns out that when you, for a lot of classification networks, and that goes for the example shown on this slide, ultimately what the first layer of your convolutional neural network is going to be learning is actually essentially how to detect edges and color contrasts. So these examples were taken from the AlexNet architecture, which we talked a bit about in last Friday's discussion. So this was a classification network, a convolutional neural network that was trained for classification on the ImageNet challenge and actually won the 2012 ImageNet challenge. So it had 96 filters in its first layer, where each filter had 3 channels for the RGB input, and then also an 11 by 11 receptive field. And so if we sort of inspect what some of these filters are doing, we can see that like these black and white filters, what those are going to activate very highly on are any portions of the image where there's like a stark edge, like a stark contrast along a specific direction. So where my cursor is here, right? So this particular filter is going to produce an activation map which has high scores in any of the portion of the image where there's that like a diagonal oriented in such a way that it kind of overlaps with this diagonal in the feature bank. And then similarly, so if we kind of inspect further down, like for example, this filter where my cursor is trying to some extent detect like a really big change in color from green to pink, right? So anywhere in the image where there's a pattern that kind of matches with this, the result of that dot product between this particular feature or this particular filter and that portion of the image will have like a very high response and correspondingly have like a very high activation within the activation map. So at the low level, we can do this. We can actually inspect what like the lowest level features are that are being learned. As you move to higher levels, so if you were to like stack together multiple convolution layers, your filters are no longer like 3 channels for RGB, right? The filters now are going to have the dimension that depends on your previous layer's output channels. So trying to visualize the filters works for the low dimensions or like the kind of early layers of the network, but it becomes much harder to actually interpret as you move deeper into the network. I'll point out there's a really interesting, it's not, actually this one might have, I think this one was published, but on today's calendar, the third reading item there is on feature visualization by Chris Ola and a few co-authors from like a distill.pub article. If you're interested in trying to interpret neural networks, that's a really, really cool article that has some great visualizations to try and interpret what some of the higher level filters are learning in a network. But for today's discussion, we'll just talk about like these early layers. Question? So yeah, so in this specific case of like the AlexNet filters, so what they would have had is not, it wouldn't be the same weight as we had in our previous slide. So instead, their filter size would have been 96 by 3 by 11 by 11. And so you could think about sort of each of those filters within the overall 96 as producing an individual sort of distinct output feature map. So in other words, what they would do is they would so you have your 96 features, your 96 filters here. Each one is 3 by 11 by 11. So the channel of 3 is the color, and then the 11 by 11 is like the height and the width that you see on the screen for these filters. So what they would do is to produce an output activation map, they would take this first filter and they would scan it across the full image, taking the dot products at every position, and that would give them a 1 by, let's say 28 by 28 feature map as output. And then they would go to the second filter in their filter bank, and they would do the same convolution across, and that would give them the second channel. So there's sort of 96 separate sliding windows, like sliding window dot product convolutions that are being applied. Yeah. So they're not only applied on images. We'll look at a couple other definitions for convolutions on like different dimensional data. So one example that we'll look at is like a 1D. You can imagine if you didn't have images, but you just had like a vector of inputs, maybe over time, you could also define a one-dimensional convolution, and we'll define it coming up. But so for example, in speech processing, if our robot's getting speech as input or just sound data as input, convolutions are also commonly applied to audio data. In addition, though, if you have volumetric data, you could define a 3D convolution. So if you have data that's coming maybe from a point cloud and you voxelize that point cloud data, you could also perform for like, if you want to do like, for example, like 3D object detection. So where you're trying to get a bounding box in 3D, not just of 2D in the pixel space. Sometimes 3D convolutions are used there. So the question was, like a lot of these filters from this AlexNet paper, they look grayscale. Like, how is it that, like, why? It's like surprising. It's like you would think that they would learn something more random or noisier maybe, but no, this is what they learned and being trained by like stochastic gradient descent. So it's surprising, right? It's sort of, but it's also pretty cool to see that they are actually picking up, like the training resulted in sort of identifiable patterns that the network is looking for, even at this very like low, at the lowest level input stage of the network. So any interpretations that we make, so like my discussion about like the fact that it's detecting edges, that's my interpretation. As far as the network's concerned, it was just minimizing a loss function according to like the convolutional layers that were defined in the architecture and then the training data that it had access to. So it's our interpretation that these edges were meaningful and that it really was like detecting quote unquote edges the way we think of edges. But yeah, so the weights were randomly initialized. So it didn't start with this knowledge. Like a human didn't give it these features to start with. All these weights initially were just like random noise vectors, maybe zero mean noise. And it happened to differentiate the different filters that it was using just through training. Right. So the question for those online was like the fact that some of these filters look black and white would indicate that the network is sort of ignoring the individual color channels at this early stage. Because if you have like a pure white pixel, then it's equally strong in all the color channels, and if you have a perfectly black pixel, it's equally weak in all the color channels. That's true for the filters that are purely black and white or grayscale. That's true. But there are filters within this filter bank, like I was saying, that actually do have color preferences. So it's not losing all of, so if all the filters within your filter bank are all pure grayscale, then you're gonna lose all the color information at the next stage of your, like at the next layer. But they don't lose all color information because they're preserving some of that with these filters that have preferences for certain color channels. Let's see, I think, yeah, another question. So yeah, so the question was, like, let's say our image is of a car, and we're trying to detect a car in an image. Is one way to think about what a convolution layer is doing is sort of redistributing the information from the 3 color channels of input into these like multiple channels in the feature space. And yes, that is the way to think about it. So like even going back, like yes, that's a way to think about it. So I think somewhere we had like this idea that so one way you can think about these activation maps is like each individual activation map is looking for one feature, but anywhere in the image. Another way to think about the activation maps is if you take any spatial location in the image, we're describing that spatial location as with a feature vector of like learned features, which would maybe be representing the car as like a set of features at this location maybe would correspond to a car. Yeah, so the filters, like the ones from that AlexNet paper, those are all learned using stochastic gradient descent. So they're initialized as just random, usually zero mean weights, like zero mean, let's say normal Gaussian. Sometimes you can use other initializers, but let's say that they're initialized with Gaussian noise as input. And then through training, I'm gonna go one more slide forward. Through training is where these actual filters that are shown are actually learned. So during stochastic gradient descent with backpropagation, you went from having random filters at the start of your training to then having these like very specialized filters that were the result after training. So in the case of AlexNet, there was never there was no knowledge of like detecting edges being baked in anywhere. The only goal of the optimization process was we set up this convolutional neural network, which is going to take in an image and output a classification score for, let's say our 10 classes of the props data set. And then we're going to define the loss to try and minimize the difference between our classification scores and the true labels. So nowhere in the training was it trying to, like, was there an incentive from the human standpoint to learn edge detection? But it just so happened that to get good at classification, the network found that having these sets of filters, which I interpret to be edges, was useful for the purposes of optimizing that loss. Oh, we have one online. Okay. What is the intuition behind using different initialization methods like Xavier distribution, Gaussian, et cetera? Like, how do we decide which ones are better? Okay. So that question is in regards to, like, I was mentioning that these filters here, and generally speaking, at the start of training, you might not know how your convolutional filter should be initialized. So in practice, what you'll do is you'll generally use some sort of randomization for initializing them. So maybe you'll initialize them from like I was saying, like a zero mean Gaussian distribution. And then the question here is like, if you have maybe different distributions that you could choose to randomize these weights, how would you decide between them? That's a hyperparameter. So generally in practice, what you would do is try multiple random initializations and then pick whichever distribution would perform the best on cross-validation. In practice, there's usually only a couple that are widely used. I think in one of the upcoming lectures we'll talk more about that. It's also still an open area of research of like understanding how some of these like initialization questions or the unique layers you're putting in your network will affect the optimization. So there's sort of like best rules of thumb, but like, so using like the chiming initializer generally is what you'll see in practice, but it's kind of beyond the scope of today's lecture. Okay, really interesting question. So there were two questions there. So the first question was, should we expect to see, if we were to somehow visualize what the filters at higher levels or sort of deeper into the network are representing, would we expect them to sort of be trying to detect higher level concepts, although we're not sure how we would measure this notion of like higher level? So the answer to that is yes, that is, generally speaking, in the context of image classification, that is what you would expect to see. I would refer you, like I was mentioning, to that distill.pub article that's linked by Chris Olah on today's lecture on the calendar. I think it's called Feature Visualization, where they actually go through and propose methods of actually visualizing what those higher level, or sort of deeper filters are actually trying to detect. But for our purposes today, it's outside the scope. But yeah, it's an interesting area of research. And then on the second question was, if you have different numbers of, if you can choose how many filters are within a specific convolution layer, and sometimes you could pick 6 filters or 100 filters. Is there a difference maybe between, I think your question was decreasing the number of filters throughout as you go deeper in the network versus keeping the same number of filters constant, something like that. So I'll sort of give this sort of a similar answer of like that also is a hyperparameter. So sort of in choosing your network architecture, you are choosing implicitly hyperparameters for these layers. So you have to pick how many convolutional layers. You would need to pick how many features within each convolutional layer. You have to pick the spatial dimension of each of the filters in a convolutional layer. So as you make those choices, some of them you're constrained. You're constrained by compute limits that you have. And then sometimes you are making specific choices about like the sparsity that you would expect to see in your data, or like the sparsity that you want in your learned features. But at a high level, I'd say it's a hyperparameter, and you have to kind of tune it. Okay, interesting. So the question then was, is there a difference between having a big layer followed by a small layer versus having maybe 2 medium-sized layers? That is very interesting. So I would say, I'm not sure I can give a concrete answer there. There's probably a whole lot of theory that would go behind a concrete answer on that, that I don't think has been fully solved yet in the context of convolutional neural networks. But I think, so generally speaking, you could evaluate the dimensionality of the input space with respect to the final output space of your variance of your networks there. And you could try and understand, is the dimensionality of the network, which is reducing, like which goes from a high dimensional to a low dimensional, is the resulting output of that network smaller in dimension than the input? In that case, it's a lossy transformation. Like you are potentially losing some information. Versus if your network keeps the same dimension from input to output, then maybe if you could also prove it can map or learn the identity transform, then maybe it's not going to be lossy. But beyond that, I don't really have an answer. Yeah. Okay. Thanks for the questions. All right, so we'll kind of go on. If more questions come up, feel free to let me know. So let's look like a little bit closer at the question of these spatial dimensions and try and understand how we could potentially compute what the expected output spatial dimensions will be for a given choice of filter size and input size. So let's say that we're that we're looking at the convolution operation applied on a 7x7 input image. So this 7x7 grid here is representing the pixels, let's say, of an input image. And then if we have chosen our filter size for one of these convolution layers to be 3x3, we could then visualize what this sliding window is going to do. So within this green 3x3 window, that's representing maybe one of the dot products that we're going to have to perform during this convolution, right? So we're sort of we're taking our 3x3 filter, we're overlapping it with this first spatial position in our image in the upper left corner of the image, and then we're going to take a dot product and get out one number. Then we'll slide our filter over one spatial position in the width direction. We'll do another dot product and get a second number that would go into our activation map. And then you would keep doing this, right? So we would do it a third time, a fourth time, and then a fifth dot product. And that's then going to decide what our output spatial dimension along the width would be. So you can imagine this same process going down the height dimension, and we'll end up as output from this first layer with a 5x5 sized activation map. And so in general, what you'll find is that with the way we've defined convolution as this sliding window of dot products, you're going to be losing spatial dimensions as you apply them. And you can actually predict how much loss you're going to have in the spatial dimensions based on the filter shape, so like the size of your filter, and also the size of your input. So in this case, for example, if you take your input size of 7x7, you subtract your filter size of 3 and add 1, that gets you 7 minus 3 is 4 plus 1 is 5. So you can see like this equation in this simple case predicts our output of 5x5. The reason this can be useful, you're probably wondering, like, why would I want an equation to predict this, is when you're setting up your neural network, sometimes it's useful to specifically ensure that your networks will like preserve the spatial dimension. And so then you're wondering, well, how could I possibly preserve the spatial dimension? What generally is done in practice is we'll do a technique called padding. So what we'll do is we'll add some data beyond the original input in the spatial dimensions, which will then ensure that our convolution, as it's performing that sliding window, will still preserve the same output shape as the input shape. So in terms of how padding is actually done, sometimes there's zero padding. So what's shown on this slide is if we were to add one row or sort of like two rows, one at the top, one at the bottom of zeros, and one column at the start and one column at the end of zeros, the result in the actual output size now, if we were to perform our convolution, would still be 7x7. And so that's important to note. The other thing then that's worth kind of considering is you can update like this equation that would predict what the output size will be to include padding according to what's shown here. This math also assumes that the filter size is an odd number. So if you're using an even size filter, the math will change. This is just like a small caveat. This is just like a useful in practice when you want to make sure that your input and output feature sizes are following what you expect. So you can, in other words, like if you know what you want your output size to be, you know what your input size is going to be, then you can tune the filter size in order to ensure that your output size is being respected. That's how you would use these equations. Okay, so one really useful term that we should be aware of is what we call the receptive field. So one thing that what we've already seen is it's a very interesting question of trying to interpret what these activation values in our activation maps, what they actually mean. So one thing that's worth sort of starting to think about, if we want to understand what those activation values mean, is to understand what was the input data that was possibly affecting those values. And so in the case of a 2D convolution neural network, we refer to the receptive field as some portion of an input image that was viewed by one of the neurons or one of the activation values within an output of the convolution layer. So in this case, let's say that we had some input image, we passed it through a convolution layer, and it produced some output activation map. If we were to then pick one of the spatial positions in our activation map, an interesting question to ask is, what was the receptive field in the original input image that was used to calculate this activation value in the activation map? And so the corresponding pixels that were used as input to calculate that activation value is what we call the receptive field. And so for a convolution with a set kernel size of k pixels, the corresponding receptive field for the input of that layer is going to be a k by k receptive field. And so the way to kind of see that is, like, if we're just thinking about a single layer of convolution, when you're calculating the output maps, right? If we want to calculate the output activation value at this portion of the map, we're doing an inner product or a dot product between this receptive field, right? This k by k, in this case like a 3 by 3 receptive field, at the overlapping spatial position of the image. So that's why the receptive field is the same size as the kernel. Things get a little bit more interesting when you try and ask, like, what was the receptive field of some feature that's maybe like 3 layers deep into your network. And so what you'll find is actually you can directly calculate, I mean, assuming you know all the size parameters of your convolutional neural network, you can actually calculate exactly what the receptive field was for every pixel in your output feature map. And generally what happens is the receptive size grows as you go deeper into the network. And the way to see that is if we imagine that we want to ask what was the receptive field for this feature within our, let's say, our third feature map, or our output feature map, you can imagine that first what you'll do is you'll go back to the preceding feature map and say, okay, well, it's the k by k receptive field that was used at this specific convolutional layer. And then for every pixel within that receptive field, you could go back another layer, and the receptive field for those features is going to grow based on the kernel size of that corresponding convolutional layer. And this same kind of happens. So it kind of propagates back as you go further back. And so if you want to calculate, for example, what the receptive field size is for a given layer, you can use this equation that's shown on the slide. Also, one thing that's really nice is there's some extensions to PyTorch where it can automatically calculate this for you. So that can be nice if you're designing like a new network architecture and you want to ensure that your network is deep enough so that the final activations maybe have seen the full image, right? So for classification, it's a great example of how you want your final activation values to have a full size receptive field so that they've actually maybe seen all of the pixels in the input image. Thinking about this is useful because what you might want to do when you're defining some of your network architecture is you bake in some of your sort of human assumptions. So in the case of classification, it's a reasonable assumption to say, I want my final classification decisions to be based on the entire image. So I want those final classification scores to have a receptive field that includes the full image. So that each score has seen every pixel for its like within all those computations that went into the final score, right? And so then all I'm pointing out here is there's actually explicit math. Like if you wanted to follow this equation, you could actually predict what the receptive field size is for arbitrary activation values at any point in your network. So it can be useful for constructing your networks. Also, though, it can be useful for debugging, to try and sort of make sure that the output you're seeing at some mid layer within your network is what you would expect. That'll make more sense once you start implementing them. So the zero padding So I guess the question was, will zero padding bleed into this receptive field discussion? So I'll point out a couple things. So the first thing, zero padding was only used at the very boundary of the image, and correspondingly, the zero padding will affect, like if at the end of the network your receptive field size was the full image, including parts of the padded portion, the padding will affect your decision. By padding data onto your image, you're basically changing what the input image was to the network. So we should expect that the classification decisions might change if you use a network that was zero padded versus not zero padded. And then in terms of like it bleeding into the receptive field, it's possible that your receptive field would include portions of that padding, of that padded region if you're using padding. So if you're using bias, for example, and you're using, and the padding, it might not be zero. Like even with zero padding, it's possible that even after the first layer, you won't have like an all zero, like that the padding won't kind of propagate. Like it's possible that first layer could, I wouldn't say ignore the padding, but maybe like mostly ignore the padding. Yeah, so can you explain what about dilated convolutions with respect to the receptive field? Okay, we'll talk about dilated convolutions coming up. We'll talk about that coming up. Okay, so one potential issue though that we're seeing with, or like one thing to kind of consider is in the case, let's say, of classification or some of these other visual tasks where we explicitly know as developers of an architecture or like inventors of an architecture that we want the final output to depend on the full receptive field, like the full input. Then one issue that comes up with convolutions is if you're moving your stride by just 1 pixel every time, then correspondingly you get just this sort of like this linear scaling in what the receptive field is going to be as you move deeper into the network. And so it might be the case that we can't afford enough convolutional layers as the way we've defined them up to this point to ensure that we still get a receptive field that includes the full input image towards the end of the network. So what we're going to use as a solution to this is we're going to start downsampling in between our convolution layers, so as a way to ensure that the receptive field grows beyond just this linear equation shown on the slide. So to look at that, what we're going to introduce is a strided convolution. And so a strided convolution is one where during our sliding window application, we don't just move by 1 pixel in the spatial dimensions, but we move by some number that's maybe greater than 1. So in this case, with the stride of 2, on this, from the first inner product we calculated to the second, we moved by 2 pixels. And so correspondingly then at the next step, we would move by another 2 pixels. And so our output size now, instead of being 5 by 5 in the case of a convolution of stride 1, now it's 3 by 3. So you can include stride in this, like as this denominator in our calculation that we saw on the previous couple slides, if you want to calculate what the expected output for a convolution layer is going to be in terms of the hyperparameters. And so another application of convolution that is, I'm going to start to move faster. So another application of convolution that's interesting is, and that you'll see actually quite a bit, is a 1-by-1 2D convolution. So imagine that we set our filters height and width to be just a 1-by-1. So now it's not like 3-by-3 filter, it's not a 5-by-5 filter, it's a 1-by-1 filter. So, and let's say that we have like 32 of these 1-by-1 filters, but we still do a 2D convolution. So if what that essentially is doing is it can be used to reduce the number of channels that your layer outputs versus what it was input. So in this case, let's say that we apply a 1-by-1 convolution with 32 filters on this data that was 56 by 56 by 64. So 64 here's the channel dimensions, 56 are the spatial height and width. What this will do is it will give us the same spatial output size. We're assuming here that like a stride of 1 in the 2D convolution, and let's say no padding. So we're still going to get 56 by 56 in the spatial output, but now what we've done is we've reduced the number of channels in our output feature volume to now 32. And so where you'll see this come up is cases where you have a convolutional neural network where maybe you want to like ensure that the number of channels of output is some fixed value, like maybe you want one channel per class. So maybe you're doing like semantic segmentation where you still want some spatial information about like over the full image. So you don't want to reduce your network down to just like a single vector of output. You still want some spatial information, but you don't want maybe 256 channels of output. Maybe you just have 10 classes that you're trying to segment. So this one-by-one convolution with a chosen number of channel outputs is a way to control how many features you have in the output. In additional, sometimes this is referred to as like a network within a network. So the paper that coined that term is cited here on this slide. And it's worth thinking about that this definition of a convolution is actually the same as essentially applying the multi-layer perceptron we talked about, but applying the multi-layer perceptron to every individual pixel within the spatial dimensions. Okay, so just a brief summary on what we've been talking about. So on the left here, this is laying out all of the hyperparameters in terms of the sizing of the convolutional layers that we looked at. So like you've got the kernel size, how many filters within a given layer, whether you're using padding, how much padding, what type of padding. So we talked about zero padding, but you could also maybe use like reflective reflective padding, where you actually like pad the image based on what is already in the image. We looked at like how you can calculate the output size for a given layer based on these hyperparameters. And then on the right-hand side, what we're showing is just some common settings that you'll generally see a lot of the time in practice. So the ones that I just want to point out, usually what you'll see are convolutions that are like 3x3, 5x5, or 1x1 in the filter spatial dimensions. Usually you don't see convolutions that are bigger than 5x5 because they get too expensive. So computationally, there's usually limits. Sometimes you'll see 7x7. In that AlexNet paper, they used 11x11 early on. So it's not that you'll never see them, but usually you'll see 3x3 and 5x5. The other thing I want to point out is that typically what's done is you'll choose the number of channels of input and output to be a power of 2. This is very practical. This is because from the standpoint of the CUDA kernel implementations, operating on data that's sized to be a power of 2 has computational benefits just because of how the CUDA library, which is a GPU acceleration library, how that was sort of structured. So you'll see 32, 64, 128, and 256, sometimes 512, 1024. Those will come up a lot in the choice of how many channels. That's not generally a choice that has some like meaning beyond just trying to get some computational gains from CUDA. But it's something to be aware of. Okay, so other types of convolution. So we looked at 2D convolution. I was mentioning also that you could define 1D convolution. So commonly in audio processing, you'll see a 1D convolution operation applied. I'm not going to spend too much time going into this because we're not going to be looking at audio data in this class, but it's something to be aware of if you are processing audio data. Another one I mentioned was a 3D convolution. So if you have some volume of data that's beyond just let's say the channel height and width, but maybe you have channel height, width, and depth, you could still apply this same idea of like a sliding window inner product. So it's still a convolution operation, but now your filters are going to be 4 dimensions. So you're going to have the channel input dimension, you're going to have some chosen spatial height, spatial width, and now also a spatial depth for each of your filters. And then also you have the number of filters that you want as output. So now it's still like a sliding window of inner products, but now your inner products are over these 4 dimensions instead of just the 3 like we were looking at in 2D convolutions. So these are even more expensive than 2D convolutions. But you do see them in practice with voxel-based data. Okay, another couple things just quickly to point out. So if you start looking into the PyTorch code, you'll find that they have implemented these common convolution layers for us. So conv2D, for example, with most of the hyperparameters that we talked about, like you can find that in the PyTorch documentation. Also, though, they have implementations for conv1D and 2D, or conv1D and 3D. So later on in this class, like once we work on the final projects, you'll be using the PyTorch implementations of these functions. But moving forward for next project 2, we're actually going to be implementing our own version of conv2D. Okay, so with that now, so that covers convolution layers. The next thing I want to talk about are pooling layers. So these are layers that can be used to downsample the data and commonly what you'll see as the benefit for that is the fact that by downsampling the data in feature space, we're effectively increasing our receptive field for neurons further down in the, deeper in the network. And so I'll just talk in this lecture briefly about the one particular type, and this is the most common type of pooling you'll see, which is called max pooling. So the idea here is we're going to still, you can still kind of think about this as like a sliding window, but instead of a sliding window of inner products, you're taking the sliding window of maximum elements. So what you would do, for example, is let's say that we have some input slice from maybe a feature map, and we're going to define this max pooling operation in this case as being like a max over each 2x2 window within this input feature map. And we're also going to assume a stride of 2. So the effect of that is this max pool, it's going to take the maximum element within this first 2x2 window. And then, then we're going to move over by a stride of 2 to this second 2x2 patch of the input feature map and take the maximum element there and store these results in our output. So the result of this 2x2 max pool with a stride of 2 is we've reduced the dimensionality, right, by a factor of 2 in each dimension. So we went from a 4x4 input now down to a 2x2 input. And one of the benefits is we can increase the receptive field for neurons maybe that would take in now this 2x2 input. We have lost information, it's true. The other benefit of this is it does introduce some invariance to small spatial shifts. So if we ignore boundary conditions, like if you imagine sort of like we slid our, where the 2x2 windowing started, ignoring boundary conditions, the max pool will be invariant to those spatial shifts. Another benefit is that from the standpoint of learning efficiency, there's no learnable parameters that we have to worry about. We just have to worry about how we control our gradients using this operation for backprop. But you'll see max pooling very, very commonly. Yeah, so the question is are there other forms of pooling, like for example, mean pooling, where you might take the average over a window? That is, mean pooling is potentially used. It is more computationally intense. It's potentially more computationally intensive depending on the implementation with max pooling. It can be used depending, to some extent, you'll see a choice between max versus mean based on the specific data and some intuition about what you want your pooling to do. So, for example, what max is preserving, right, is sort of just the strongest activations. But it might be the case that you actually want an average of activations over a spatial location, and you might reason about that based on the data set. So, so you can use some intuition there, but also your choice of pooling function, whether it's max or mean or some other function, is also a hyperparameter. So it's also common to see people test out multiple different versions. Mm-hmm. Okay, so that's just that was a very brief, very, very brief overview of pooling. And we just looked at max pooling. Another question? Mm-hmm. Yes, so the question was, we would apply pooling, for example, after a convolutional layer, and then we would still include a nonlinear activation function. Yes. Yeah, so in the case of ReLU, so let's say after we applied max pool, if we were to then pass this output to ReLU, it would take ReLU of element 6 and then place that in the output element corresponding to that spatial location. Then it would take the ReLU over the input 8 and place that. So you do element-wise activation. I'm not sure I fully understand. You're saying if one of the elements in this output of a max pool is 0, then that would mean that the maximum element within the corresponding window that was the receptive field for that were all either 0 or less than 0. And so it's not necessarily meaning that you're ignoring that part of the image, but maybe it's saying that for this specific feature that's trying to be detected at this layer, it had very low activation at this spatial position of the input. Right, it would be done for every filter that you're using. Yep. Okay, so just a brief summary here. Yeah, commonly what you'll see used is max pool with a 2x2 kernel size and a stride of 2 in both spatial dimensions. So that has the effect of what we saw. It's going to reduce the output by a factor of 2 in the height and a factor of 2 in the width in terms of dimensionality. Sometimes you'll see variants of that. You might see 4, like a kernel size of 4 and a spatial stride of 4, but usually 2 and 2. Okay, so now we've built up like what's a fully connected layer. We saw the benefit of activation functions for fully connected layers. Today we were looking at convolutional layers and pooling layers. So we actually have all the tools we need now to start building up what is one of kind of the classic or kind of core architectures that you'll see in CNN applications. And so this core architecture that's very common is where you would perform the following set of operations. So you'll have a 2D convolutional layer, then a ReLU activation, then a max pool, and you'll have some n of those 3 chained together. So you'll sort of stack up n of those conv, ReLU, pool layers. Then you'll flatten the resulting vector that you get as the output of your final convolution layer there, and then pass it to some number of fully connected layers before having your final linear classifier produce your output. So one example of where this classic architecture was used was in the seminal paper from Jan LeCun in 1998, where they were looking at performing document recognition using a trained neural network. So we'll sort of step through this architecture and see that we have all the tools we need to actually implement it. So so the input to this architecture was a binary image. So they had an image of 1 by 28 pixels by 28 pixels. So that would come in as input. And then they had a conv ReLU layer that would take in that 28 by 28 pixel image and produce a 20 by 28 by 28 sized output feature map. So here what they had was 20 individual filters within their filter bank. Each of them had a 5 by 5 receptive field and 1 channel based on the fact that the input was 1 channel. Then they had a max pool operation. So they had a 2 by 2 max pool with a stride of 2. So that reduced the size in both the vertical and the horizontal spatial dimensions by a factor of 2. And then they kept on with another convolutional ReLU layer with this time 50 channels of output. So each of these filters was a 20 channel for the 20 channels of input it was getting from the preceding layer, and then a 5 by 5 in the spatial dimension. But then there were 50 of those for these 50 output activation maps. And then moving forward, there was another max pool to reduce it down further spatially before finally, I think there was a set of 2 linear layers with a ReLU in between to produce their final activation function. So their final activations, because they were trying to classify for, I think it was 10 classes, is going to output a final size that's going to be like a vector of size 10. And so a couple takeaways we can have from this example. The first is we're seeing that within these network architectures, the spatial size over time, as you progress deeper into the network, it decreases, right? And so the way to see that is, like if you come up here, the original input was 28 by 28, but as we have these max pool operations, it reduces down the spatial size to first 14 by 14 and then ultimately 7 by 7. So we're getting smaller and smaller in the spatial size. At the same time, though, because they added an increasing number of filters throughout the network, the channel size increased as we got deeper, right? So we started out with just 1 channel of binary input, but then we had 20 filters in the first convolutional layer, 50 in the second, and I think there was just that second one, right? So one thing, though, to note is that because the total sort of volume was roughly preserved, the amount of computation through these layers is also roughly preserved. So that's a trend that you'll see in a lot of 2D convolutional networks. It's the fact that as your spatial size decreases, you'll usually add an additional number of channels, mostly because you can afford to. But there are some modern architectures where that's not the case, and actually they'll try and have like a smaller number of channels as you get deeper. But as a general trend, these spatial size decreases over time and number of channels increases usually holds true. Okay, one problem that sort of sets up for next lecture is that these networks, as you can see, we're adding more and more parameters, and the actual like structure of these architectures is getting more sparse, and to some extent we could say maybe more complex. So it becomes increasingly hard to train these networks, even with stochastic gradient descent. So there's been a set of work that actually tries to improve the training efficiency of these algorithms using normalization. So I'm not going to go into this today, but there's a technique that's very, very commonly used called batch normalization, which tries to ensure that at every layer of your network, the input to that specific layer is going to be zero mean and unit variance on distribution. So we'll talk more in next lecture about why this was beneficial. And in addition, next time what we're going to talk about are some common CNN architectures that and what we can learn from them. So kind of tracing like the history of CNN architectures up to this point, because you can see it's a relatively new kind of paradigm, right? So that first ImageNet winner, for example, being in 2012. Having said that, though, the last thing I do want to reserve like these last 4 minutes for is just kind of going a little bit more into detail about what to expect for the final project. So the final project, it's going to be a research-oriented final project. So it's going to be instead of an exam, which is good. And the goal for this project from our standpoint is to give you all experience with what it would be like working in the area of research for deep learning. Because this field is so new and growing so much that it's very likely if you do work with deep learning, you're going to be very, very close to the research end of it. Because on the practical side, like we talked about in discussion, so many of the practical implementations of deep learning are dependent on what the state of the art is. And the state of the art is always changing. So hopefully in this project, you'll get some experience with reading the literature, reproducing published results, and then also proposing a new idea that you could test on some data. And so at a high level, these are really the kind of the core pieces that go into research, right? You have to understand the field. You have to trust what the field has produced, right? So you have to be able to reproduce results that already exist. And then you have to have the skills needed to actually propose some new idea and then maybe more importantly, test how that new idea works. So this is going to be a group-based final project. So you'll be able to work in teams from 1 to 3 people. So if you want to do that by yourself, that's totally okay. But if you would like to work with a group, that's, we'll facilitate that. In terms of what to expect in terms of like the deliverables, so there's going to be 5 deliverables that are going to be distributed out over time. So there's not going to be like one big deadline where all 5 are due. Instead, it's going to flow. So first there will be a paper review, which I'll talk more about. So this will be where you'll read one of the core papers that we've identified on the website, and then write a review about how that paper addresses a specific problem within the field, what others have already done within that area of the field, what ideas maybe or what work is left to do based on that specific paper's contributions. Then on that same paper, you'll give an in-class presentation. So that'll be during the seminar style. So starting from week 8 on in the class is when we'll have these in-class paper presentations. And then from there, 3, 4, and 5 are more on the technical side. So 3, 4, and 5, the deliverables are first going to be to reproduce some results from a published deep learning and robot perception paper, and then to extend that result using either like a new idea, this could be like a new network architecture or a new layer, maybe some new technique to do some analysis. So maybe like you would want to visualize what some published network is actually learning using feature visualization, or maybe try a network on a new data set. So any of these, and we can talk more about potential ideas for how to extend a paper, would go into deliverable number 4. And then the final written report would be the 5th deliverable, which would come then at the end of the semester. So just going like a little bit more into detail here. So final project teams, we're going to base them on overlapping interest. So we'll open sometime early next week, like a quiz. It'll be one of the 16 total quizzes where you can put in your area of interest. We'll leave the quiz open for, I think, like 3 or 4 weeks. So you have time to go through the papers and get some sense of what the different areas are and where you're most interested in. So each team, after everyone has filled out like what of the core papers they're most interested in, each team will be assigned based on the the overlap of their interests. The paper review then will be due like 1 week before the presentations take place. And so the presentations are going to be broken down based on the topic. So on our course schedule, starting from week 8 on, you'll see there's topics and then corresponding papers to go with each of those topics. So the scheduling, for example, of like the RGBD papers, like those presentations will come first because that's in week 8. So as you're going through the paper list, think about also like when the scheduling would happen if you're worried about potential scheduling conflicts, or come and let us know if you have scheduling conflicts. And with, I think, like 1 minute I have left, on the paper reproduction and extension, I'll talk more about this at next lecture. Don't worry too much about this. Like, what does it mean to reproduce the results of a paper? We're not looking to completely reproduce all of the results because that can very possibly be too much. But maybe like a core result from the paper you could reproduce and then use that reproduction that you've done to then extend it, like I said, maybe using some new data set or some new layer, and then evaluating what your extension ultimately resulted in. So the project report then is like a 1 to 2 page paper covering these core topics of what you've done in the project. And the grading breakdown is also published on the syllabus for this. So these are the 5 deliverables with the corresponding breakdown. And we'll talk more about this in next lecture, but I wanted to give a bit more clarity about what to expect for this project coming up. With that, I'll see you at discussion tomorrow and have a good day.